Hi everyone, my name is Maxime Bouton and today I'm going to present our work on reinforcement learning with iterative reasoning for merging in dense traffic. This is a collaboration between the Honda Research Institute and the Stanford Intelligent Systems Laboratory. Road fatalities represent about 1.35 million of deaths each year worldwide, and most of the serious crashes are caused by human error. So the promises of autonomous driving is that by assisting human in performing certain maneuver or removing the human from the loop, we could have much safer roads. Autonomous driving is a very complex problem that can often be decomposed between perception, feedback control, motion planning, decision-making, and route planning. Today, we're going to focus on decision-making. Decision-making is a part of the autonomy stack that's responsible for taking as input the information from the perception system and convert it into action. And it has to do so in a time frame of between 0.1 to 1 second. Some common driving situations are still challenging for autonomous vehicles today. For example, this merging scenario in dense traffic. It's a crowded scenario. You have many vehicles to consider in a restricted area. There might be unexpected behaviors, and our ego vehicle in blue might be confronted to a variety of behaviors. To address these issues, some previous works proposed to use hand-engineered rule-based methods. Those requires anticipating every situation, and they're hence difficult to scale to complex scenarios. One could use online search instead. Online search usually requires a lot of online computation, so they're not always suitable to put on board of a vehicle. And because of this computational burden, one often needs to rely on simplistic driver models. So they're difficult to scale to dense traffic scenarios. Reinforcement learning, on the other hand, is very scalable and allow you to use a very flexible model for the environment, but it requires a lot of interactions that must be performed in simulation. And it is also known to overfit to the training environment. In the talk today, we'll try to show you how we overcome some of the challenges around reinforcement learning for autonomous driving. In particular, we're interested in two aspects. The first one is designing the training environment. How do we not overfit to a wrong driver model? And what models to use for other human drivers? Can we learn those models at the same time as we learn a policy for our ego vehicle? And we'll also look at the credit assignment problem. In autonomous driving, actions can often lead to deadlocks or collisions, and they often require long-term reasoning. It takes several seconds to perform a maneuver. And all those aspects are enhanced in dense traffic because cars are much closer to each other and it takes much longer to maneuver. We will see how we can perform an efficient curriculum to avoid the standard problem in reinforcement learning. The key ideas of our approach is to use level K reasoning to model human drivers and to develop a curriculum learning using each reasoning level as an intermediate task for our reinforcement learning agent. This will allow us to train the agent against a variety of drivers for more efficient and robust policies. We're interested in the following problem. The ego vehicle in blue must change lane in dense traffic, and the vehicle in front is blocking the road, so it has a limited distance to perform the maneuver, and other drivers might have different behaviors and stochastic behaviors. Our goal is to generate a lane change policy using reinforcement learning. In this work, we are modeling the environment by a partially observable Markov decision process. So it requires a transition model and an observation model. We're in the context of model-free reinforcement learning, where our agent is interacting with a black box simulator. And the policy of our agent will be represented by a neural network. And we'll use a standard deep Q-learning algorithm to train our agent. So to fully define our reinforcement learning problem, we need to see what's the input and output of our policy. So let's first look at the observation space. The ego vehicle observes its own state, position and velocity, as well as heading. And it can also observe the position and velocity of other vehicles, but only within a range of 30 meters due to sensor limitation. And in addition to that constraint, we'll limit the number of vehicles to observe to a maximum of 8. So the ego vehicle in blue will always observe like the 8 closest vehicle, or less if there aren't 8 vehicles in the 30-meter range. For the action space, we have a very high-level design that's composed of lateral and longitudinal actions. The longitudinal actions consist of 3 possible desired speeds. Those desired speeds are then converted into acceleration using the intelligent driver model. So this longitudinal action has some safety constraint embedded in it, thanks to this intelligent driver model. For the lateral action, our agent will have the choice between change lane or keep lane. If it decides to change lane, then this will be converted to a lateral acceleration using a PD controller. It's a total of 6 actions by combining those 2 action spaces. And those actions are high level. And we found that using high level actions was really helpful in learning policies faster. Our policy is represented by a neural network and is trained using deep Q-learning. We used a neural network architecture from an existing work by Hoel et al. We were able to reproduce the result that this architecture, relying on convolutional neural network, lead to more efficient policy and faster training than using simple dense layers. So with the current observation space and action space, we can train a policy against noisy rule-based drivers. We found that it can learn a better policy than just simple rule-based method. But this setup is not ideal because we still don't know how the policy would perform against smarter driver, because the human driver model that we're using in the simulation is overly simplistic. Moreover, some behaviors are completely missing from the training environment. So for example, this scenario is so dense that most of the time the rule-based policy are not able to perform merging from the right to the left lane. To overcome the challenges, we propose to use iterative reasoning for both designing new human driver models and designing a curriculum learning to learn policies faster and learn more robust policies. Iterative reasoning is this intuitive concept of I think that you think that I think. It's formalized using the level K behavior model, which can be explained as follows. There is a level 0 behavior model, which does not assume anything about the environment. A level 1 behavior model will assume that all the other drivers are following a level 0 model. Level 2 model assumes that everyone else is following level 1, and so on and so on. So the idea is that by populating a scene with those different cognitive levels, we can create variety in the training environment. So we propose to use this idea to design a curriculum for our reinforcement learning agent. The curriculum will alternate between learning merging policy and keep lane policy. So in level 1, our agent will learn to merge against level 0 drivers. In level 2, we're training the policy for the green car. So it's a keep lane policy. And it's going to be trained against both level 0 and level 1 drivers. So in this new level, now it has blue cars that are trying to merge in front of it. We can then go to level 3, which is learning to merge for the purple car against both level 0, level 1, and level 2 drivers. And we can keep increasing the cognitive level to create more challenging scenarios and more variety in the driving behaviors. To summarize this curriculum idea, so at each level of the curriculum, the agent experiences all of the driving styles from the previous stages. The curriculum alternates between learning to merge and learning to keep lane. So we have one different task for each level. And what's important to know is that to initialize the curriculum at level 0, we use a driver model that follow a rule-based model from the literature. So intelligent driver model for the longitudinal control and mobile for the lane change policy. Both of those models are parametric, and we draw the model parameters from a distribution to still have some variety even at level 0. So for each of the tasks of the curriculum, we need to design a reward function. They're very similar and follow a relatively simple structure. There is a penalty for collisions, a penalty for deviating from a desired velocity to encourage the vehicle to move. A fixed reward for passing the blocked vehicle. So this is when the scenario is completed. For the merging task, in addition to that, we'll add a reward for being in a new lane to incentivize the vehicle to change lane. Right. So let's discuss our experiments. So we implemented simulation environment in Julia using the open source simulator Automotive Simulator.jl. And each level of the curriculum takes about 1 hour to train on a single CPU. And we used 1 million interaction with the simulator for each level. We trained policy up to level 5 in the curriculum. So since we're alternating between merging and keep lane tasks, this leads to 3 merge policies and 2 keep lane policies. At training, we train in both sparse and dense traffic. However, when we evaluate the policy, we evaluate in dense traffic only. For evaluation, we also set a timeout at 40 seconds. So if the ego vehicle has not passed the blocked vehicle within 40 seconds, a timeout is declared. Otherwise, an episode can either end in a success when we pass a blocked vehicle or a collision. Here is a demonstration of the policy. So the blue car is a level 1 driver, the purple car is a level 2 driver, and the green car is a level 3 driver. So we can see that with this curriculum, we can have emerging interesting negotiating behavior, especially between the green and the purple car. So the purple car has experienced drivers that are merging in front of it, and hence it has a more aggressive behavior. The blue car has not experienced that aggressive drivers, and so it's not able to cut in front of the purple car because it has a lower cognitive level. For the quantitative results, we evaluate each cognitive level against each other. So in this table, we report the percentage of success, where the rows correspond to the policy level being evaluated. So 0 is rule-based, and then 1, 3, 5 are merging policy, and 2 and 4 are keep lane policies. And in the columns of this table, this is the cognitive level of the environment. So an environment of level 3 will have drivers for all of the lower levels, so 0, 1, 2, and 3. What we can see from that table is that hand-engineered policies, level 0, do not perform well at all because this environment is very challenging. The cars are about 2 meters apart. So it requires a lot of negotiations which are hard to encode in rule-based system. Level 1 is standard reinforcement learning and performs much better. So it's outperformed by level 3 and 5, especially against unseen behavior. So if we look at level 3, for example, level 3 against level 5 will have about 91% successes, whereas level 1 only has 85% successes in this scenario. And it's important to know that the level 3 policy has never experienced a level 5 or level 4 policy, but it's still able to outperform level 1 because overall, since it's a higher cognitive level, it has experienced a broader variety of driver behaviors during training. Some possible extension to this work, we tried first to transfer the policy to another simulator to see if it was robust to model discrepancies, both in the dynamics of the ego vehicle and of the driver model. And we were able to get interesting results where without any retraining, the policy was able to successfully complete merge maneuvers in this completely different simulator, which is higher fidelity. Natural next step would be to do some real-world testing, see if our policy can directly transfer to real world. We're also interested in combining those reinforcement learning policies with online planners, like the work of Hubman et al. These reinforcement learning policies could be used to estimate the cost to go in the leaves of the tree. It would be also interesting to combine this policy with safe reinforcement learning approaches to have some stronger safety guarantees. To conclude this presentation, here are the 3 takeaways of this work. First of all, designing the training environment is important when applying reinforcement learning to autonomous driving problems. It can overfit to the driver model that you're using. We can use iterative reasoning to address this problem by designing a training curriculum, and it will help generating a variety of driver behaviors. And finally, the policies trained against more diverse behaviors generalize better to behaviors unseen during training.